All right, today we're going to talk about zero knowledge proofs. I think it's one of the most important technologies out there for providing both proof of some particular thing, like you have an account balance that's sufficient to transfer funds, or proof of authenticity, and at the same time, preserving privacy. Zcash is based on zero knowledge proofs. But before we get there, I want to talk a little bit about some things that are in the news right now. Two of these have to do with fingerprint readers. Remember that a fingerprint is not really a password because you can't change your fingerprint. So it's more like a username. But we're using lots of fingerprint readers on our phones and things for providing security. There's a nice article in Ars Technica, which I've listed there, that shows that a dedicated attacker has about an 80% success in faking people's fingerprints and being able to break into something like a phone. There's another article there about using a master fingerprint that has all the characteristics you are looking for to be able to fake machine learning that is based on unlocking fingerprints. And both of these also fail to take into account really the fact that we have had tremendous leaks in fingerprint databases. For instance, the Office of Personnel for the United States government lost pretty much its entire database, probably to Chinese hackers, about a year ago, of all of their biometrics data and all of their personal data on some 60% of all United States government employees. So this data is out there in the wild and it can be faked. Another thing that's in the news is that tokens are being used, and I've got a link there, for tracking, or actually what they call contact tracing with privacy on the coronavirus. I think that is a good thing. And it turns out that a large portion of the Ethereum network has joined Fold at Home to participate in looking for a cure for the coronavirus. And the way that they're doing this is that there is a good chunk of time on most of these Ethereum miners where it's not actually solving the problems of mining a coin. This is the in-between time in each transaction. And they're actually using primarily that chunk of time to participate in Fold at Home. There's about 6,000 systems with GPUs out there working on this. So zk-SNARK. It's an acronym. The ZK part is zero knowledge, and we're going to go through some examples of zero knowledge. And it basically is a proof that you have some piece of knowledge or some value that you can demonstrate, and you're not going to give that away, but at the same time you're going to prove using some mathematics or some system that you have it. So you can prove it without sending it. Think of it this way. This is the most common use of it today, and we're actually going to get to this, is that it can allow you to prove that you possess a password to something without ever transmitting that password to a server. So you could have a login where you know the password, but the server has never ever seen the password and it's never been transmitted. That's actually a common use case for this. And in that case, you have security that doesn't expose the server to loss of the passwords or loss of the critical information. So as a system administrator, this is a really good thing, because now if you have this data, basically, if you don't have the user's passwords, then you can't expose them. It's no longer a question of did you use the right hashing method, and did you encrypt it, and did you lose a copy of your database like Ashley Madison did, and did you do all of your security right. If you use a zero knowledge proof system, they have their password and they keep their password. And you only have some math that allows you to verify that they still possess the password. The particular use case for this is SRP6A, and it's based on the Schnorr identification algorithm. We're going to go through that, I believe. But first of all, let's step back and take a little bit higher look at how zero-knowledge proofs work and why they work. And we're also going to go through an interactive example. There is a general-purpose way of taking information in an algorithm and converting it to a zero-knowledge proof, one of these SNarks. The SNark part is the succinct, non-interactive argument of knowledge. Non-interactive means that instead of the zero-knowledge proof requiring that you send a request, get a response, send a request, get a response, send a request, get a response, and in each iteration you increase the level of knowledge, the non-interactive means that you can just send a single request and demonstrate that you have this knowledge. In the case of SRP6A, it actually requires 3 requests to both prove that the user has the password and to prove that the server is the correct server back to the user. At which point both sides can have an encryption key that they can use for encryption that is created from the process, and that encryption key has never been transmitted between the client and the server. So a man in the middle can never see the encryption key. And given that you can build from this base encryption key using a hashing algorithm a strong encryption key that's suitable for something like AES 128 or 256-bit encryption, or a number of other encryption schemes, basically you can set up a communication channel between two people with one of these zero-knowledge proofs where both sides can then encrypt their data, nobody can listen in between, and they have never sent the key back and forth, which is a marvelous thing, just absolutely marvelous. So, in a general purpose zk-SNARK, you have some sort of a computation in step 1. This is like, I have enough funds in my account to buy this particular item. You create from that an algebraic circuit. Basically, that algebraic circuit takes the computation and compiles it into a bit of code, okay, is what we're actually going to end up here. And that bit of code is going to be provable and usable in this construct. Once you have the algebraic circuit, you produce one of these R1CS constraint systems. And this is basically converting the algebraic circuit into a set of vectors. You convert that set of vectors into a QAP, a quadratic arithmetic program, and you then use a linear prover over that to do an interactive proof. Now, because the proof is over the space of all possible polynomials, a single random value run through this proof as input shows that you are in possession of the correct polynomial. So a single iteration of I have a random value and I can prove what the result of that random value is now provides the zero knowledge in a succinct fashion. Which, when you think about it, since the number of potential polynomials in 2 space is infinite, and you can pick out a single point in this infinite series and say, yeah, for this value, here's the solution, means that you have a very quick way of doing the proof. Now, all of these 7 steps that set up the zk-SNARK are relatively difficult. I mean, we've got some sort of complex computation, we've got compilation, we've got translation of that compilation into vectors, we've got taking the vectors and making this QAP, quadratic arithmetic program, that then has to be normalized into another form requiring a complex, what do you want to call it, synthetic division process. The synthetic division process requires a symbolic computation, and its functions are very difficult to do, and at the end of this we have an interactive proof. So this is a non-trivial thing. There's a reference at the bottom of today's handout for the tech's paper on this that describes this process in detail. And I don't know if we're actually going to go through this process. Because basically there's a lot of math in this and there's a lot of pieces, and it relies on a lot of different things. An implementation of this would be a very valuable thing for many, many applications to start out with. Yeah, you can put in this piece of algebra at the beginning, you can get a zk-SNARK out the bottom, and figuring out how to do that efficiently. So this is a very active field of research, and it's something that the Ethereum Foundation is working very hard on right now. So this is not just an idle thing. This is how to turn a smart contract into a zero-knowledge proof and be able to demonstrate lots of things about it. Now, one of the nice things about this is it fits well in a mathematical model of how smart contracts work. If you look at the data for smart contracts, the input is a fixed set of data, as in 12,000 or 11,000 Ethereum nodes all have the same initial data at the same moment in time. And there's no outside data that a contract can see. So this is a known state. A particular smart contract function, a method, is called, and that method acts as a transformation on some of that input data, plus some outside input data, the parameters to that method, which are fixed and agreed upon at the time that the transaction is run. So we have existing data plus new parameters. It does something to the data, and at the end of this, all 11,000 computers produce a known new state output. So if you look at this from a graph perspective, what you have is you have a giant deterministic finite automata, where the edge across the automata is the method inside the smart contract. And the nodes in this automata are the different states that you can be in. And that turns out to be very useful for proving things about the nature of the contracts themselves. It also points to the pure functional nature of smart contracts, where you have a known state, you make a transition, at the end you come to a new state. But it also means that there are tremendous limits on the smart contracts too. It means that when you have a smart contract, this thing can't go out and say, generate a random number by itself, because in the process of generating random numbers, if it's random across different nodes in the network, everybody's going to get a different result at the end. If it's going to be a random number generation, you either have to have something like a known oracle that everybody is going to refer to, or you have to have a system that allows people to generate that random number in a consistent fashion across multiple nodes. And there are systems like that. So this pure functional nature of the data and the pure functional transition means that you have a very different kind of computation system than you would otherwise. Now, this is not the only kind of a thing out there that is a pure functional kind of a system.